Okay, everyone, welcome to week 17 of quantum field theory. Today, we're going to look at the weak interaction. Okay, so I think I'm going to spend this week and next week talking about weak interactions because we haven't really discussed them. And actually probing QCD and probing quark and gluon dynamics, you guys may have seen in some of our exploration, a lot of that probing happens through the weak interactions, okay? So this is a good chance for us to sort of peer into this, see how it all works. Today, I'm going to sort of just show you the basics of the weak interaction. I'm going to show you the Feynman rules and that kind of thing. I won't derive the... Okay, yeah, thank you for that. I will pin my... Oh, no, it says it's pinned.
Oh, my bad.
Oh, spotlight.
Oh, yeah. Because when I click on the speaker view.
Yes, there we go. Now it's good. Yes, good. Okay, so today I'll sort of show you the basics of the weak interaction, the Feynman rules and all of that kind of thing. And next week, we will do electroweak unification. So that will take us the whole lecture. Electroweak unification being the major achievement of Glashow, Weinberg, and Salam. Mainly Glashow, but that is sort of a nice, it's a difficult topic, but it's a good topic to look at. But we'll try. I'll try to simplify it as much as possible. But it's a challenging topic. But we'll look at it since it's such a big achievement of 20th century physics. And if you want to look that up, that's called the GSW model. People usually write it. Or I don't know, something like that. If you just look up electroweak unification, which showed that the electromagnetic forces really are derived from weak interactions, that there's a unified underlying structure to that, which was quite a big achievement. Okay, let's get started on that then. The homework. So there's quite a little bit of papers I want you to look at. So the first thing is LB chapter 47. Okay, and this is in addition because there was 2 weeks of reading in the document, right? So, get that done too. And then there's 2 papers I want you to look at. The first paper is by Feynman and Gelman. So these are sort of 2, if you can't get these, let me know. I'll send you PDFs. Okay, because I know with the access sometimes, right? It's okay, and this is called Theory of the Fermi interaction, and you'll see why it's called this. This was written in 1958. And the second paper, and actually these 2 guys won the Nobel Prize for this. So T.D. Lee and C.N. Yang, who you know Yang from Yang-Mills theory. And they won the Nobel Prize. And it's called Question of Parity conservation in the weak interaction. So parity conservation in this was written in 1956. So these are 2 very iconic papers. There's like those classic Gelman and Lowe's papers. There's many classic papers in QFT. These 2 are very classic papers, and they have thousands of citations. And obviously Feynman, Gelman, all Nobel Prize winners. Gelman worked a lot on QCD. We know Feynman and Lee and Yang. This paper is extremely famous because this but it sort of, there was an experimenter who proved that parity was violated by the weak interaction. And she was a woman, and she did not win the Nobel Prize with Li and Yang, which is ridiculous. Everyone thinks she should have won it. They only gave it to Li and Yang, which is crazy. But anyways, so this paper was the first theoretical paper that sort of postulated the idea of parity violation, which we know is violated by the weak interaction. And this paper, you'll see where this paper comes from, the basic idea of today. But please read these because it's very good to see the historical papers. I like assigning them. Okay, let's get started. So do you know the mediating particles of the weak interaction? What are the force mediating particles?
The W and Z bosons.
Exactly. So the mediating particles, so I'll erase this actually, of the weak interaction. So that will be our place to start. And it's actually the major difference. You'll see why it's called the weak interaction. But the major difference is the W and Z bosons. So W plus or minus, and then the Z boson is a neutral boson. The key to the weak interaction is that these guys are massive, right? We know that the mediating particles in the strong force, the gluons, the mediating particles in QED, the photons are massless, right? And so that is the major, that's why this is called the weak interaction, quote unquote. It's because actually the mediating particles are massive and actually pretty massive by the kinds of scales that we are talking about. Okay, so they're a massive spin 1 particle, right? And they have 3 allowed polarizations. So any massive spin 1 particle has 3 allowed polarizations, 1, 0, and -1. How many allowed polarizations does the photon have? A massless spin 1 particle. Two, right? Exactly. So there's 1 extra degree of freedom we have to just take into account. So let's work that out. So remember, the first condition we put on the photons for the polarization was that epsilon mu p mu equals 0. All right, that was the very first condition. And that reduced the number of degrees of freedom from 4 to 3, just by imposing this condition. Okay, then in the case of photons, we also imposed Coulomb gauge. So Coulomb gauge was epsilon 0 equals 0. That's just the condition for Coulomb gauge. And the fact that epsilon dot p equals 0. And this reduced the number of degrees of freedom for epsilon mu from 3 to 2 or 4 to 2. So we imposed Coulomb gauge for the photon, but this condition is enough for the W and Z bosons because they have 3 possible helicities. Okay, so that's the basic, if you want to call it a gauge condition or whatever. So, okay, let's write down the propagator. So remember, in QED, the propagator went minus I G mu nu over Q squared, right? Where Q is just the internal momenta. All right, that was the basic, where G mu nu is the Minkowski metric. Sorry, I use G and eta kind of hand in hand. And if you wanted to work out the S matrix, you would find that in the weak interaction, you get a propagator minus I G mu nu minus I times Q mu nu minus Q mu Q nu over M squared. Okay, so we get a little bit of a different numerator over the standard sort of pole Q squared now minus M squared. Right here, I also have Q squared minus M squared, but since the photon is massless, the M doesn't, make a difference. So this is the W and Z propagator. Now we often work in a very nice limit for the weak interaction where Q squared is much less than M squared because these bosons are so massive. And so really we often just write the propagator as minus I G mu nu. Then we don't even need that term. And we can just keep this bottom term. That's really what we usually write the propagator as. Oh, sorry, not Q squared, M squared, right? Right? Not Q squared. So that's usually what I'll write the propagator as, just because we can usually just keep this limit because the W and Z bosons are massive. Okay, so let's write down a vertex factor, right? That's sort of the next step that we usually do, this kind of thing. So we have some, we'll use dash lines for the W and Z bosons, right? We have like curly lines for the gluon and then like a wavy line for the photon. So the last line left is a dash. And we'll call this a W minus. Let's look at interactions with the W minus first. And let's say we have some lepton, call it L minus. Could be any kind of a meson or an electron. And it gives off some neutrino. So that's the thing. That's one of the most common weak, so we'll call this the neutrino. So remember, one of the most common interactions that's a weak interaction is a particle giving off a neutrino. Okay, that is the most common weak interaction. And to each lepton gets assigned a neutrino. So the muon gets a muon neutrino. You may have heard of this, right? When you see the standard model. The tau gets a tau neutrino. So this is the most common sort of interaction, quote unquote, we can have. And we'll have some vertex factor, right, for the mediating particle. So let's write down that vertex factor. So this is just what? This is just lepton neutrino to lepton plus W minus. Okay. That's what this is. And remember, we could also have a variety of different reactions, right? We could have an anti-lepton and the anti-neutrino. We could have all kinds of crossed reactions with crossing symmetry, exchanging the sign. So here's the vertex factor. Now the vertex factor for the weak interaction is what is so weird. So you have minus I GW, where GW is what I'm going to call the weak coupling. Okay. That's just my convention. These two root 2's are convention times gamma mu, 1 minus gamma 5. Okay, so that is the vertex factor. And so this stuff is fine. This guy is just basically what we keep seeing popping up with vertex factors, right? Gamma mu is fine. That tells me that the coupling's a vector coupling, because in QED, remember, the coupling was included a gamma mu d mu. Now this guy is what's weird, this 1 minus gamma 5. And actually what you'll see is that this, first of all, this 1 minus gamma 5, this combination of gamma matrices, gamma mu, gamma 5, is what we call an axial vector coupling. Okay. And the reason that historically people couldn't figure out whether it needed to be an axial vector coupling, they realized it had to be an axial vector coupling to account for parity violation, which we'll show. And actually that's what that paper by Gelman and Feynman is about. So Feynman and Gelman were the first guys to say, look, we probably need an axial vector coupling to describe the weak interaction. So that's where this originates from. So if you look at that paper, they actually write this coupling down for the first time and play out the consequences. Okay, it turns out that the coupling goes like 4 pi times alpha W, where alpha is just the fine structure constant. So I forget what it's like 1 over 137. Okay, cool. Shall we compute an amplitude? I think that's probably the next step. Okay, let's do an amplitude. I'm only going to work out one amplitude in total today. The rest, I'm just going to write down the cross section. Okay. So I'll do one amplitude. I mean, it's really not that different, right? It's really not that different. It's all the same Feynman rules, and it's just the basic thing. But let's do one, and then we're going to look at some of the different phenomena. So let's take a look at the process. Muon neutrino plus electron goes to electron neutrino plus muon. Okay, that will be the process. So let's draw the Feynman diagram. Call this P1, we'll call this P3, we'll call this the electron. Let me see how I want to do this. Yeah, we'll call this the electron neutrino. We have an internal line, another vertex. Right, so now the internal, the virtual particle that's exchanging the force is the W boson. We're looking at negative interactions for now. So, and some internal momentum Q, right? This is the muon neutrino. This is the muon, right? And we'll say this is P2 and P4. So I'll give you a second to write down the amplitude. Right, and just remember, so Q equals P1 minus P3, yeah. And we'll work in the limit, again, where Q squared is much less than M squared, right? Which is the basic kind of like weak interaction limit. And we'll call this MW for W boson, just because it's a different mass than the Z. Okay, so I'll give you a second, work that out, and then I'll give you the answer. So remember, we want an expression for the amplitude. Okay, let me write it down. So we have two vertex factors, so we're going to get like GW squared over 8 times MW squared, right? That's just from the two vertex factors. Okay, and then we have some spinors, right? So we have one, they're all particles, no antiparticles. So they're all going to have U's, right? That's the thing. So I have some U of P1. Okay. Then I have that vertex factor. So the axial electric coupling, gamma mu1 minus gamma 5 times U bar of, I'm just going to write the numbers. So U bar of 3. We'll do it in the basic like spinor helicity language where we just write the numbers. Okay. So that takes care of all of that. I have my propagator. Oh, I need a propagator, right? One propagator, right? For the internal stuff. Actually, wait a second. This handles the propagator, right? Because this MW squared pops out. I don't need the Q squared term, right? That drops out because I'm working in that limit. Yeah, okay. So then I get one more term. I get some like U of 2. Gamma mu 1 minus gamma 5 U bar of 4. That's it, right? Yeah, this is okay. This is the easy part. Now let's do our basic procedure where we sum over the spins, use the trace rules, do all of that, annoying stuff, which when we did QED, if you're confused, you watch that lecture because we did that really slow, but I'm just going to do it fast today. When you've done these long enough, you can just stare and then get the answer. So I need some sum over the spins, right, of obviously M squared, right? That's the whole idea now. So the easy part, EW squared over 8 MW squared, that's the easy part, right? Okay, so trace gamma mu times 1 minus gamma 5. Okay, that's okay. Right, okay, this one's actually not bad. P/1 plus ME, I'm just using the trace properties. Gamma mu, 1 minus gamma 5, P/3. Done. So that's the first term, right? Because this P1 is massive. So it gets some mass term, right? But then the neutrino, the P/3 does not get any mass term, right? Because neutrinos are practically massless for our intents and purposes. Okay. Okay. Times. Now I have to translate this term, right? Using the trace rules. Because I just did this term, now let's do this term. It's the same game. So times trace, gamma mu, 1 minus gamma 5. And now this time the massless particle is going to be 2. So I get like P/2, right? This should be a lower index actually. It's going to contract with that guy. And then I get some gamma mu, 1 minus gamma 5. And then I need from this guy. So then I get what? I get P/4 plus M mu. Okay, that's the second step. So let's work out the traces. By the way, like even if you're really confused, right? You should go into the book and like you did Jenna, where you followed all the spinor helicity. You should follow the steps for these kinds of things, because if you can do this kind of calculation, you can calculate any basic amplitude, at least at tree level, right? Right, this is all there is to it. It's just the trace properties and that kind of thing. And then at loop level, let's not even talk about it. We know what happens at loop level. We have a lot of issues. Okay, so let's evaluate the traces. I'm just going to rewrite this term up top. Right, so then the sum over the spins, I'm just rewriting this guy. M squared PW squared over 8 MW squared squared. All right, great. Okay, let's evaluate the first trace, okay? So I'm gonna call this first term, so we'll call this first term rho. We'll call this second trace term sigma. So let's evaluate rho. So rho equal, I always like to do that because then it's easy. I just like labeling them. So rho is just what? I'm gonna get an 8, P mu 1, P mu 3. I'm just using the trace properties. Plus P mu 1, P mu 3. Once you start getting the patterns, it's actually pretty easy. Minus G mu nu, P1 dot P3. minus I epsilon mu nu lambda sigma. Epsilon is just the standard like 4 index Levi-Civita, and we get some P1 lambda, P3 sigma. That's the first trace. Now the second trace, so sigma, I get an 8 again, but now I'm going to have sort of the same expression, just with the 2s and 4s, right? So P2 mu, P4 mu, minus G mu lower, P2 dot P4. Minus I epsilon mu nu, we'll call it chi tau, chi tau, P2 chi, P4 tau. Okay, that's just using the trace properties. So we're going to make use of the following, oh no, I have the epsilon. We're going to make use of the following identity between Levi-Civitas, which is a nice one, four index Levi-Civitas. And that is that epsilon mu nu lambda sigma, epsilon mu nu chi tau can be just written as a series of Kronecker deltas. That's a useful technique. So 2 delta chi lambda. Let me just make sure I'm going to do this right. Delta sigma tau delta lambda tau. I'm going to need one more. Just let me just make sure what indices I'm missing. Delta sigma chi, right? And using this identity now, I can just basically, and then multiplying everything out, which is a pain, you can write down that the sum over the spins, let me just do it really quick, is the following. So remember, now I just have to multiply rho times sigma, right? And then turn the crank. That's the easy part. It's tedious, but it's easy.
In sigma or in rho, didn't you have another P1, P3 term that you didn't have in sigma, like at the beginning?
In sigma and in rho. Oh yeah, I'm missing a term. You're right. What am I missing here? Yeah, good catch. I'm missing a P2 nu, P4 mu. There, sorry. Good catch. Yeah, absolutely. Okay, good. Okay, so let's write down the final expression. So we're going to get some 4GW over MW to the fourth. P1 dot P2, it's a very simple expression, actually. You just think about it, P3 dot P4. Okay. So that's what we get when we sort of wrap everything up. Let's write down a cross section. This should be very kind of like, you know, you're looking at this having seen some spinor helicity, right? This should be very like suggestive that you can write down general amplitudes as just dot products of momentas, right? If you ignore the mass, right? So this is a nice kind of thing. Because like it's no surprise you get such a nice simple answer, right? It's kind of nice. Okay, so I hope this was somewhat instructive. It wasn't a waste of time. I would go through all the algebra slowly and look up the trace properties, see where it's all coming from. Okay, let's just write. I'll just write down the cross section. That's not really a difficult thing to do now, because we have once we have mu squared, we can write down m squared. Sorry. Can write down a cross section. So d sigma d omega. So let's write down some differential cross section. 1/2 w squared e 4 pi mw squared squared 1 minus mu over 2e squared squared. Should be squared again, if I remember correctly. But check that, okay, but this looks similar to some of the QCD stuff that I've been putting in the document, some of the cross section, except there's some cosines and sines, which we'll be introduced to today, why they come up. Okay, so actually the first person to try and come up with a theory of a weak interaction, really a beta decay interaction, was Fermi, right? And Fermi wrote the first paper on the weak interaction, on his theory of the weak interaction in 1933. And he had the following diagram. So this is what Fermi, I mean, he didn't draw a Feynman diagram, but this is what he was describing. He said that you would have some E go to mu, right? And then give off muon neutrino and an electron neutrino. But he did not have any massive virtual particle. He just had a direct 4-particle coupling. Okay, that was what Fermi thought was the correct theory. And it didn't work, obviously. The cross sections didn't match up. A lot of this stuff was not correct. So people had an inkling. So this was, we'll just write down. So this is Fermi. This was Fermi's theory in 1933. So it became apparent that something had to resolve this, right? Okay, let's look at another very famous sort of weak interaction process, okay, i.e. Pion decay. So Pion decay is a very famous process in the weak interaction that students look at. The Pion decay, okay? So Pion decay is the process where the pion decays into some lepton plus that corresponding neutrino. Okay, now here's the thing. Now I can describe the pion, sorry, this is pi minus. I can describe the pion as quarks, right? It's made up of quarks. So we can describe this weak interaction in the following way. So let's write out what channel am I about to draw, the S, T, or U channel? T channel. You know a good way to remember it? S side, T top, and then U is crossed. That's a good way to remember it. Okay, so let's just work out the S channel diagram. Okay, so you have some lepton neutrino. You have some outgoing lepton. You have a vertex here. You have some W boson, W minus boson propagating that way. And now the pion I can write down as 2 quarks, down quark and an up quark. It's a meson. Right? Mesons are made up of 2 quarks, right? Nucleons are made up of 3. Okay, so that's the Feynman diagram for this process. Okay, now we don't really, I haven't really told you, or we don't really know how these quarks couple, right, to the W boson. That's mysterious. We're not going to get there, and we actually don't even need to know that for this procedure. So let's redraw this diagram, and this is sort of the way it's taught when you learn, because you learn the weak interaction in a particle physics class before the strong interaction. So they don't show you, and the coupling is not important. So the classic way this is taught, you have some pion now, I just wanted to show you that this is why we can talk about quarks in the weak interaction. You have some coupling, we'll call this blob coupling to the W boson. Okay, so now the blob is some coupling, and then there's a vertex factor. And then there's just your standard vertex factor where the neutrino, oh, actually, wait a second. I think this goes to, this is an anti-neutrino. Sorry, that's why this arrow, I'm like, why am I drawing this arrow? Because this is an outgoing anti-neutrino, okay? And this is an anti-quark. Okay, that makes sense. Right, because the arrows are flipped, because those are both ingoing. Okay, sorry about that. That's a quick semantic thing. And then you have, again, the anti-neutrino corresponding to the lepton, and a vertex factor. Okay. And we'll say this has momentum P2, this has momentum P3. Okay. So we've seen blobs like this before, right? When we drew out sort of like, when I wrote out the schematic for you for a general scattering amplitude, right? And these are just called form factors, right? And we can write them as just functions f mu with some factors. They're just form factors. Okay, so I'll give you a second to write down the amplitude, except this time, we're going to call this blob the form factor f mu, and we're going to say it's equal to f pi times p mu. So it's just some constant that's proportional to the momenta, because that's the vertex factor has to be, right? Because any vertex factor, so f mu, has to be proportional to p mu, right? And then we have some constant of proportionality, right? That's just, and this is actually going to be called the Pion Decay constant. So you get some actually rate of decay from this calculation. Okay, so I'll give you a second to write down the amplitude. It's really kind of simple because now you only have to worry about P2 and P3, right? There's only one term. So take a second and just write down that term. So I'll just get you started. So of course, this coupling is just GW squared over 8 pi MW squared, right? That's from the vertex factor and the propagator. And then you're just going to get one term for the amplitude. So I'll give you a second to write that down. Okay, so let's write that down. So we have some like U bar of 3, the outgoing particle, gamma mu lowered, times 1 minus gamma phi, times what? V, because it's an outgoing anti-neutrino, V of 2, all times F mu. Right, that's just the amplitude. Okay, can I erase the board or are we still? Okay. Okay, so let's just write down the cross section. I'm not going to do the whole trace stuff. That you can work that out, and then you can confirm that you get the following expression for mu squared, for m squared. So m squared becomes the following. So you should check this, that you get GW over MW fourth. Sorry, 2MW. F pi squared ml squared, mass of the lepton. M pi squared minus ml squared. And so you should just confirm that that's what you get. And we can write down the decay rate, gamma. So any decay rate is defined in the following way. You can look up this formula. It's just equal to P. So the absolute value of all the momenta over 8 pi h bar. I'm only writing the h bars here because it's an exact formula, m squared c times m squared. And so you can compute now the decay rate from this expression we just derived. And yeah, and you can write it down. I'm not going to write it down. It's a simple thing because I just gave you m squared. Just plug it in. Okay, I'll write it down for you anyway. Just so we're on the same page. So f pi squared, right? Over pi h bar m pi squared GW over 4 MW to the fourth ML squared m pi squared minus ml squared squared. And that's the decay rate. So there's a very interesting thing that people calculate using these decay rates. You may have heard of the term branching ratio. You ever heard of that in your reading? Okay. The branching ratio tells me sort of the relationship between the decay rates of two different processes. So you're finding relationships between decay rates of two different processes in the hopes of learning more about the physics. So one very famous branching ratio that people sort of wrote down was gamma of this process. So pi minus what we just computed, pi minus to E minus plus electron neutrino. And they compare that to the decay rate of pi minus to a muon neutrino. Sorry, these should both be anti. I don't know why I keep doing that. And this is called a branching ratio. And they found that this was 1.2, some number, 1.24. I have the number written down, 1.28 times 10 to the minus 4. This is what theory predicted. So this is theory for this branching ratio from just computing the amplitudes and using all the numbers, right, instead of the letters. And experiment found that this branching ratio was pretty close. 1.23 plus or minus 0.02 times 10 to the minus 4. This is experiment. So they match pretty good. Pretty good match, right? So now the question is why is there a discrepancy? Okay, so that's what I leave to you. So why do you think there is a discrepancy between the two processes? In other words, what is this branching ratio telling me? Does anyone have any inkling of this? And this is kind of an interesting point to understand because it sort of will help you frame a lot of the different things that you're going to look at. You can take a bad guess, it's fine. It's okay, we only have 40 viewers anyway. It's not. So let me guide you through it. I have a pion, okay? Jenna, I give you a pion in the lab. Do you know what it's going to decay into beforehand? No, there's different probabilities, right? That it might go to an electron or it might go to a muon. That's the beauty of this. That's where this quantum mechanics stuff comes in. And this tells you what process is more likely, right, than the other. Right? So that's what this is. It's telling me, is it more likely for the pion to go to an electron or a muon?
A muon? Or
the muon, exactly. Exactly. Okay, so that's a good thing. So you can always kind of do these little things. You can compute two different amplitudes. Of course, the masses are going to be different. That's going to impact the final result. And it's subtle, but it's not that subtle. Okay, so that's a nice little exercise. Take two random weak interactions, compute the amplitude, and see the branching ratio and see if you can get it to match. That's kind of a fun exercise to do. You may even discover that some processes are totally suppressed. You know, this ratio was still kind of close. It was almost close to 0, basically, or close to 1, sorry. No. Yeah, it was close. It was like 1.28 times 10 to the minus 4. So it was pretty small. Okay, great. Hey, let's talk a little bit about the weak interactions of quarks. Okay, let's dig into that a little bit. So if I have leptons, so I have an E electron neutrino, I have a muon, I have a muon neutrino, I have a tau, I have a tau neutrino. So 3 generations of leptons. Okay. Oh, we call these generations, okay? That's a particle physics word. You may have seen that word, so. In the weak interaction between the leptons, it's all in the family. An electron can only go to an electron neutrino. A muon can only go to a muon neutrino. A tau can only go to a tau neutrino. There's no mixing, okay? So leptons couple to the W bosons in the same generation. Okay, that's a nice little thing. Quarks are runts. They don't do that. they mix and they couple with each other, and we have to see this is where these angles are going to come in, or these thetas. They tell us how to mix these different things. They give us a little parameter to multiply by that alters the amplitude. Okay. So we have 3 generations of quarks, up, down. That's the first generation. And by generation, it really means they're organized by mass, right? By mass. That's what we mean by generation. Charm, strange, and top bottom. Okay, these are the 3 generations of quarks. Okay, so people started to realize that the quarks and the weak interaction did not stay all in the family, so to speak, right? That their various processes were intergenerational. And so there was a great physicist in 1963. So in 1963, we only knew that up-down and strange quarks existed. So we only had up-down and strange quarks. And his name was Cabibbo, who Gell-Mann talks about a lot, actually. And so Cabibbo postulated that if I had the process down goes to up plus W plus, sorry, W minus, that it would carry a factor of cosine theta. We'll put a little subscript C. And if S goes to up plus W minus, so now intergenerational, then I get sine theta C. Now, in effect, sine theta, cosine theta is just multiplying by some number. It's just an extra factor that's going to take us from one to the other. Okay, so the vertex factors now, so this vertex factor is just minus I GW over 2 root 2 gamma mu 1 minus gamma 5 cosine theta C. So that's the new vertex factor. And then this one is the same thing. So minus I GW 2 root 2 gamma mu 1 minus gamma 5 sine theta C. Okay, so that's what Cabibbo postulated. And experimentally, this angle, this Cabibbo angle, is 13.1 degrees. Yeah, so that's where the C, Cabibbo. So this started working for many, many processes. It was like, wow, you know, you add this silly parameter and the amplitudes work, and you can account for the intergenerational mixing of the quarks in the weak interaction. Until one day, some experimenter tried the following. They decayed a K naught into a mu plus mu minus. And they found that the Cabibbo prescription gave you the wrong answer by a factor of 10. It seemed as though, you know, because, see, this is why, you know, when people say in science, okay, what are the truths of science? I say absolutely nothing. Because so they're doing all these experiments. Cabibbo's theory works. I mean, look, it works. It's good. They do this random thing and it's completely off. So they had to come up with some solution for this. Okay, so they found that actually the amplitude was now proportional to a factor of sine times cosine theta times this Cabibbo angle. So who came to the rescue in 1970? Sheldon Glashow. You can tell Glashow did a lot of incredible work at this time. I mean, there were many people, but. So Glashow comes up with the solution to this. Now, okay, you have to keep this in perspective. People were still on the fence at this time whether the weak interaction was axial coupling. As Jetta knows, people were still on the fence at this time whether quarks existed, right? Like people, this is not, so there was, the whole weak interaction program felt a little speculative at this point, even though the experiment matched theory, but people didn't really know if quarks were a thing. They didn't know if what was actually accounting for was this phenomenon. So a lot of speculation. And then on top of that, now you have this issue. And when I tell you Glashow's solution, people were even more skeptical. What was Glashow's solution? He introduced a new quark. So his solution was even more crazy. And all of these people working on the weak interaction, led by Glashow and Salam and Weinberg, they seem a little bit on the fence because he had to introduce a new quark. So Glashow's solution in 1970, so you can read this paper. It's called the GIM mechanism. So GIM mechanism. And quote unquote, Glashow was the first author. And it's called, and they introduced the top quark. So the top quark was introduced. Oh, sorry, not the top quark, the charm quark. Oh my gosh, sorry, charm quark. So this was 4 years. Okay, so in 1970 was 4 years before they actually discovered the charm quark. Okay, and they predicted the mass, and I'm going to show you the right vertex factors, the right coupling. But can you imagine? They were left on the hook if this thing was real. When they found it, can you imagine the relief? Yes, this works. And there's a special name if you look it up. 1974, when they found the charm quark, was referred to as the November Revolution, because that's when they found all of these quarks, all of the whole sort of apparatus of the standard model. And this was all at the LHC, not the LHC, sorry. It was all at CERN. They didn't have an LHC at that time. They had a smaller collider, but it was all at CERN. Okay, so let's write down the right coupling. It seems trivial, but at the time, it was introducing a new particle. That's not really trivial when you don't even know if the quarks really exist. So again, it's coupled to a W minus. And now we just get a minus I W 2 over root 2, gamma mu 1 minus gamma 5, but minus sine theta C. Okay, so now mu m is proportional to minus sine theta C cosine theta C. And if you just couple this now to a strange quark, now you get a factor of cosine instead of minus sine. Okay, so we'll just write this as upper strange, and we'll put this as sine theta or cosine. Let's see. That's the coupling. Oh, sorry, not up, down. What am I doing? Down. Because they all have different masses, so it's very important to distinguish them. Okay. This is kind of a big deal. I mean, this was crazy. At 1970, people thought this was crazy. First of all, we don't know if these exist. Now you're just saying there's another one. Seemed like string theory. Okay. Okay, great. All right, so we can go, now we can go between sort of generations of quarks. So I'm going to erase, I'll keep it. So if I have some D prime, some new quark, I can now write the new quark as a superposition of the old quarks, D cosine theta C plus S sine theta C. All right, and if I have some S prime, I can write this as, sorry, this should, yeah, minus D cosine theta C plus S sine theta C. Oh no, this should, no, sorry. This should be minus D sine theta C plus S cosine theta C. Okay, I can put this into a matrix. This will be useful. So I have the following matrix equation. Okay, so I can put this into some matrix that looks like this. Matrix equation. And so now this D prime and S prime are referred to as Cabibbo rotated states. They're superpositions of quark states. They're Cabibbo rotated states. They're not actual quarks, right? So this is for down and strange quarks. Okay, and two Japanese physicists, Kobayashi and Masakawa, generalized this argument to show the mixing of all quarks. And this is the Kobayashi-Masakawa matrix. It's some long thing. I'm not going to write it down, but it's just all of the different combinations. It's not so important. And of course, each combination gives you a different number, different parameter, okay? So that's the big thing. So the GIM mechanism. I forget the other two guys, Glashow. Okay. So 1961, which I should have had you read this paper, but I'll send it to you guys. 1961, Glashow writes the first paper postulating the idea of electroweak unification. Who gave him this idea? I watched an interview of Sheldon Glashow. You should watch it. Amazing interview with Lawrence Krauss. The only interview I know of him on YouTube. It's not really. He's still alive. Actually, all these guys are pretty much alive except Salam, which is kind of cool. So, and he's talking about how he gets the idea. So Lawrence Krauss, so wait a second. So he goes, so he calls him Shelley. So I guess they're on a personal basis. He goes, Shelley, how did you get the idea for electroweak unification, right? That seems like such a, he said it wasn't my idea. He said it wasn't my idea. And Lawrence goes, whose idea? He said it was Schwinger's idea. I was shocked by this. So he goes, so Sheldon Glashow was a PhD student of Julian Schwinger at Harvard. Schwinger taught at Harvard for many, many years. And he had many graduate students that wanted to work with him. And he had a line of 20 graduate students. This is the story. And Schwinger was going down the line and giving each graduate student an idea. Can you imagine, for a thesis right there on the spot? And he gets to Glashow and he goes, Glashow was the last one. And he goes, I want you to look and see if there's a way to unify the electromagnetic forces under the weak interaction. Amazing. He just said it in one sentence. I mean, he had that much intuition. And it's what propelled his career, what he worked on for 20 years, what he won the Nobel Prize on, all of that. And it was very interesting hearing that from him. He said, it wasn't my idea, it was Schwinger's idea. Very interesting. Just goes to show you, these guys had many, many, and then you look at the Gell-Mann-Feynman paper. People just think Feynman retired after QED. No, he made a lot of contributions. You know, the public doesn't know about this. And Gell-Mann made a ton of them too. So it's just interesting to think about that sometimes. Okay, great. So he publishes this in 1961. In 1967, Steven Weinberg and Abdus Salam come through, and they say that actually Sheldon Glashow's electroweak unification scheme is actually a spontaneously broken gauge theory. Oh, by the way, that reminds me, for next week, if you're not comfortable with spontaneous symmetry breaking, get comfortable with it. You're going to need to know that process, finding the minimum and all of that. By the way, Mansour, Steven Weinberg, and Sheldon Glashow both went to your high school and graduated in the same year from your high school, Bronx Science. There's a very interesting story. Steven Weinberg and Sheldon Glashow, same high school, Mansour's high school. And they both wanted to go to the same PhD program. But Weinberg went to Princeton, got into Princeton, got rejected from Harvard. And Glashow got rejected from Princeton, got into Harvard. So they flip-flop.
I'm pretty sure when you walk in, there's like a poster with them on it.
I'm sure. I mean, they're titans. They're like two of the greats. So that's really cool that they were both in the same year. Can you imagine the kinds of conversations they were having? It's pretty cool. It's pretty wild. And both won the Nobel Prize in the same year. Can you imagine two high school buddies winning the Nobel Prize in the same year for the same? I mean, it's just an unbelievable. Too bad the public doesn't. If you ask the public who is Steven Weinberg or Sheldon, they don't even know. So that's the thing. You have to promote this. Okay, anyway, so that happens in 1967. And then in 1971, we had another wunderkind, Gerard 't Hooft, who proved that the theory was renormalizable. And not only that theory, but all non-abelian gauge theories, for which he also won the Nobel Prize in 1999. So this was a very this was an extremely exciting time from the 1940s to the 1980s in theoretical physics. That 40-year stretch, extremely exciting. From 1940 to 1980, tons of developments. Okay, anyways. But no experiment until 1973 at CERN, which was the November Revolution. Okay, anyways, so let's now look at neutral interactions, okay, which are a little different. So let's have an anti-muon neutrino go to an electron. Oh, what am I writing down? Plus an electron. Going to an anti-electron neutrino plus a muon. Oh, no, sorry. This is a neutral interaction plus an electron. No. A muon neutrino plus an electron. So in the neutral interactions, they can actually give off a different neutrino, but it doesn't make a difference in your calculation. You don't need that extra factor because of the fact that the mediating particle is different. Sorry. Okay, let's draw the Feynman. Do I have to draw the Feynman diagram? All right, I'll draw the Feynman. Fine, I'll draw the Feynman diagram for you guys. There was a very old quantum field theorist that made a joke. He said, "I'm a professor of Feynman diagrams." That's probably not accurate. Okay, that is not accurate, sorry. Okay, so this one's going out, this one's going in, this one's going out. This electron's going in, this electron's going out. Okay. And now the vertex factor is now minus I, we'll call this GZ for the coupling to the Z boson, which is neutral, over 2 times gamma mu. And now we get some weird mess here. By the way, in that 1961 paper, Glashow postulated that you must have neutral interactions. So that was a prediction that was made. Okay, we'll call this CVF. I'll tell you what these are. CV, what the heck? What do I want to call this? If I call that CVF, okay, we'll call this CAF. I'll tell you what that means in a second. Some factors times gamma 5. So these two guys depend on the quark and the lepton and quark involved. Okay, they're constants that are going to depend on what particles you put in. So that's how the vertex factor differs. Let's not worry about that really. Okay, but you get some factors. Wait, can I erase this board? We're going to see where these come from, but it's going to take us a little bit. Okay, so in the Glashow, Salam, and Weinberg model, all of the numbers or all of the parameters that the theory depends on one sort of angle. You can call it it's not really an angle, theta W. You can derive everything from this one number. And this is called the Weinberg angle or the weak mixing angle. So you have the relationship now between the coupling for the W and Z boson to the electric charge. So GW equals GE over sine theta Weinberg. This stuff's not going to make any sense until next week because we're going to derive all of it from the electroweak unification. Then you have this relationship, GZ equals GE over cosine. Sorry, sine theta, cosine theta. Okay, so you have electroweak unification by this parameter theta W. Where does it come from? You'll find out when I show you electroweak unification, what the model actually looks like. Turns out experimentally that this Weinberg angle is equal to 28.7 degrees. Why is it that number? Nobody knows. This is a big challenge actually for people. You see, the standard model has a lot of parameters. You probably are starting to recognize it. Like when you see the standard model on someone's t-shirt, there's tons of parameters that are random, seemingly. And one of the big challenges of people who try to come up with so-called grand unified theories is to derive these parameters, right? In principle, a grand unified theory should be able to derive these parameters. No one has been able to derive this Weinberg angle. It's a big challenge. Yeah. One of the earliest examples of a grand unified theory was also actually Sheldon Glashow with a guy named Howard Georgi, which was an SU5 grand unified theory, and even they couldn't derive this. So it's very interesting, actually. Okay, let's write down a few more relationships. So the Z propagator then is just, we'll just write it down, minus I J mu over Q mu Q mu. That's just the Z propagator over MZ squared. This should be, should be a minus. All over Q squared minus MZ squared. And right, we work in that limit. So we get minus I G mu over MZ squared. Okay. And the relationship between the W and Z masses is that MW equals MZ cosine theta. That's the relationship between the masses. Okay, so these are actually the basic predictions from the unified model, GSW, right? This prediction, and this should be theta W. This prediction, these two relationships, and this Weinberg angle. And you can derive all of the relationships of the weak interactions from the GSW model. Okay, that's all I have for today. I hope today was relatively simple. We just did some kind of straightforward calculation. I didn't really show you. Next week's going to be difficult. I'm giving you fair warning. So if you do some reading, that will help you a lot. And please review spontaneous symmetry raking. Or the lecture I gave on it, because that will be important. Let me just stop recording.